Okay. So over the weekend, I reviewed all of the tests, or at least those tests for which the score was not already 100, and assigned partial credit where I could. So overall, the scores were quite high. So after partial credits taken into consideration, the median was actually 100. So more than half the class got 100%, and then the mean turned out to be a 94, just for reference. There were so this test is 25% of your grade. The and then we have homework, one more test coming up down the road, and then the final, and that's everything. So this is I don't believe I have this in writing in the syllabus, but just to give everyone more of a better chance to have a good overall grade, what I tend to do, and I'm happy to do in this class, is after you take a final exam, if your final exam score is higher than either one of your test 1 or test 2 scores, then I can use it to replace that lowest test score. So again, only if it helps. So then basically the test you do better on will count for more of your grade. So I tried to set it up so that basically there's always hope. So if test 1 did not turn out as well as you would like, then there's still plenty more of it you could do. Still lots of opportunity to get a better overall grade in the end. Okay. But if you have any questions about that, feel free to shoot me an email. Okay, so we're getting further into or getting out of the way the rest of section 2.1 on matrix operations that I started on Wednesday. So there's one operation that comes up in a couple of problems in this section, and we'll certainly be seeing a whole lot more of. That's called the transpose of a matrix. So I'll get the screen share going. Okay. So I need to say a few words about the transpose before I jump into the problems. So let's suppose we have a matrix A that is m by n. So m rows, n columns. Then the transpose of A, and the way we denote it is A with a T as a superscript. But I will mention it may be denoted differently, like in other books. So sometimes I like to use a uppercase T. Some use a lowercase, or some use an asterisk, which for a more general concept of transpose called the adjoint. So either one of these can be used. I've seen used to refer to the transpose. Is a matrix with the opposite dimensions. So A is m by n. A transpose is n by m. So how it is defined, first I'll give a formula. So the ij entry of the transpose is just the ji entry of A. Okay. So informally, you get to transpose by reversing a sense of rows and columns. So the rows of A are the columns of A transpose and vice versa. So I'll just make up a matrix as a, well, actually, I'll just take one from one of the problems. I like to find one that's not square. Okay. Okay. All right, so here's our matrix A. Then A transpose. All right, so to fill in the first row of a transpose, I just take the first column of A. And then I keep going. So then, okay. So here, first row of A, first column of A transpose. Second row of A, second column of A transpose, in that order. Okay. Now, so here's some important properties of the transpose. Okay, first, if I take a transpose of a matrix, and then I take the transpose of that, then I just get the original matrix A back. Because here rows become columns, and then columns become rows. We're back where we started. Next, the transpose of a sum of matrices is just the sum of a transpose. So you can take a transposes individually and add them together. Now that is, you have to be careful though if you have the transpose of a product. So what if I have, let's assume that it makes sense to multiply A and B. So in other words, the operation is well defined for the A and B that we have. And then we want to take a transpose of a result. So in this case, it's not just A transpose, B transpose. It's close to that though. You got to reverse the order. So it's B transpose, A transpose. So transpose of a product is the product of transposes in reverse order. Okay. All right, here are some useful terms related to transpose. All right, the inner product of two matrices is A transpose B, where a transpose is in between A and B, so it's on the inside. The outer product is where the transpose is on the outside of the matrices involved, so A, B transpose. Now I should mention about the inner product. This is equivalent to an operation that you are familiar with from calculus and possibly other classes. is the same as a dot product if A and B happen to be column vectors. So if A and B are column vectors, and by convention we often write vectors as columns, then this is the same as a dot product operation where you're multiplying corresponding elements to the vectors and then adding them all up. And we'll see more of these operations when we get to the problems. Okay, a matrix is symmetric if A is equal to its own transpose. So A has to be a square matrix for that to happen. And sure enough, A would have a symmetric appearance that basically there's symmetry across the main diagonal. Okay. And then it's called a skew symmetric matrix. That's where A is equal to minus its own transpose. Okay. So when we get towards the end of the problems here, some of these things will come up again. All right. Now, one thing that's very different when multiplying matrices and vectors as opposed to multiplying numbers, that when you're just multiplying numbers, if a product turns out to be 0, the only way that can happen is if one of the numbers you're multiplying is 0. But with matrices and vectors, it's possible to have, for instance, multiplying two non-zero matrices or multiplying a non-zero matrix and a non-zero vector and still get 0 as a result. So this problem here we have a non-zero matrix, and what it's asking for is finding a 2 by 2 matrix so that A times B, which is also a 2 by 2 matrix, will turn out to be 0. So this gets to something you dealt with in the first chapter, and that is solving systems of equations in which the right-hand side is the 0 vector and coming up with a non-trivial solution. So what I'm going to do is find a matrix B that makes this happen, and if it's not unique. Like if I find a B that works, I can multiply B by any constant. I can even multiply it by certain matrices and still get 0 as a result. But all it's requiring is that you make sure that the matrix B you enter as your answer has different non-zero columns. And the thing is, certainly I can multiply A by 0 and get 0, but I want to find a non-zero matrix that works. So what I'll do is find we're going to get a system of equations that characterizes the entries of this matrix. But what we'll end up doing is finding B one column at a time. So first this column and then this column. Okay. So if I write out the product of this A and this B, all right, so here's A times B written out. Actually, let's move this to a new page. Okay. Okay. So what I've done here is I've actually carried out the multiplication of the matrices A and B. So here I have, I'm going across this first row of A and first column of B, carrying out the multiplication to get the 1, 1 entry of the result. So 2 times B1, 1 minus 4 B2, 1. Same thing over here. I'm taking this, going across this row of A, this column of B, and multiplying corresponding entries and adding them up. So 2 times B12 minus 4 B22. If I repeat the same thing for the second row of a result by using a second row of A, multiplied with the first column of B to get this, and then with the second column of B to get this entry. So then all 4 of these entries must be 0. All right. Sorry, my computer's acting up. Okay. All right. Now from these 4 expressions, all equaling 0, I'm going to get systems of equations. So I'm going to focus on these 2 entries because they deal with the first column of B, because we have B11, B21. Once we focus on these to get the first column, then we move over to these and get the second column in the same way. All right, so first column, we have a system of 2 equations set equal to 0. So just taking first column of these. Here we have a matrix equation. So here I'm taking the first column of a matrix equation. Okay. Now, notice that these 2 equations are very closely related. All I got to do is take this first equation and multiply it by -2, and I get the second equation. So really what we have is 2 equivalent equations. So we just only need to solve the first one. Now, if I have 1 equation, but 2 unknowns, I have a free variable. So I can, for instance, set B21 equal to, I can designate that as a free variable. So let's go ahead and set it to 1. All right. So if I set B21 equal to 1 in here, then I can solve for B11. So if this term is going to be -4, this term has to equal 4, so B11 turns out to be 2. So from that 1 equation, I get the first column of my non-zero matrix B. Now, you can think of this system as being like any other system that we've dealt with, where you could take the matrix of coefficients and row reduce it. And what would happen is, because this equation is equal to -2 times this one, this row would be all zeros. You'd only have this equation left. This is your free variable. Okay. So then, if I proceed to the second column of B, well, that's going to be the same system of equations. The unknowns are different because it's the second column versus the first, but the coefficient matrix, like whatever it actually be row reducing, is exactly the same. So really, the only way I can get a different column here is to choose a different value for my free variable. So this is unfolding the same way so far. So what I do is I just set, here's my free variable, B22, just as B21 was a free variable last time. Instead of setting it to 1, like last time, I'll just set it equal to 2. So then whatever I said, B22 equal, this free variable equal to, this variable will be twice that. So I get B12 is equal to 4. So now we have a second column. So any column I get for B is going to have its form, or this first entry is equal to twice the second entry. It all depends what it is. It just depends on what I set my free variable equal to. So then I can put the two columns together. 2, 1 is my first column, 4, 2 is my second column. So this is a suitable matrix B that satisfies A times B is equal to 0. But really, I can put anything in here as long as whatever entry I have in the first row is equal to twice the entry right below it. That's because it's this equation that determines what entries of B would work. So, questions about this one? Now next we have a matrix multiplication problem of a different sort. We're given a matrix A, and then we're given a product A times B, but we're not given B. So the idea here is to find at least first two columns of a matrix B that would produce this product. Now, A is 2 by 2, AB is 2 by 3. So for this product to make sense, B has to have 3 columns like a result, and it has to have 2 rows because A has 2 columns, just by the laws of matrix multiplication. So B is a 2 by 3 matrix. So what I can do is I'm going to do this one column at a time. So because the first column of the result is just A times the first column of B, which is unknown. And then the second column of AB is just the whole matrix A times whatever the second column of B is. Now, I'll make a comment here. If my product AB, which is equal to A times, if I write out B in terms of its columns, B1, B2, B3, we know there are 3 of them. Then to get to product, it's just taking A, multiplying it by each of the 3 columns in turn. So just A, B1, A, B2, A, B3. Okay. So this is one property of matrix multiplication that we can take advantage of. That here we know what the first column result is, -5, -6. And we also know the first column result has to be A times B1, whatever B1 is. And then similar for the second column of a result. So what this gives us is two systems of equations to solve involving A. Like before, we were solving AX equals B, and that's what we have here. This is our right-hand side, which we normally refer to as B. The solution, which we normally call X, the solution to this system is the first column of B. The solution to this system is the second column of B. So to get the first column, we'll just work with the this augmented matrix. So A and then the result, AB1. So take a matrix A here, first column of a product here, and now when I solve this system, I'll get B1. So I can do what I always do with an augmented matrix, and that is row operations. So if I take this row and add to it 4 times this row, and fortunately, since such a small matrix, that'll be enough to get it into echelon form. But for convenience, I'll just take this second row and divide it by minus 13, just to make the rest of the solution process easier. All right. So now I can just go ahead and solve this system using the usual process of back substitution. So here we have a second equation, and remember these are right-hand side values, and I'm solving for the first column of B. So here I have, this is the first, whoops, my indices are, well, it should be 2, 1. So this is second row, first column of B. First row, first column of B. So B11, B21, those together make up my first column. So now I can just right-hand side value divided by coefficient, and then here I have right-hand side value subtracting off this coefficient times the unknown from a previous equation. So I'm substituting this into this first equation and then dividing by this coefficient. So now I have my first column of B. Now, I just have to repeat the process for the second column. And all of that's going to work out the same. Only this last column of the augmented matrix has changed. Sorry, that should be AB2. Okay. Now, the row operations are determined only by the coefficient matrix. So the row operations are no different. And so I'll do the same thing as before, where I divide the second row by minus 13. And that's my final augmented matrix in echelon form. So then I could use back substitution again. And I'm going after the entries in column 2. So that's why the second index is equal to 2. So second row, second column, first row, second column. So then I go for the same process of substitution as I've shown in various problems from chapter 1. So right-hand side value minus these terms with the previous unknown substituted in. And then we get our entries 1 in the second row and then 5 in the first row. So that gives the second column of B, 5, 1. Now, it's not required for this problem, but if I were to take the third column of B and solve the same kind of system, same row operations, same everything, then I would specify B completely. But all that's required here is just get these first two columns. So using the fact that each column of a product is the entire first matrix times the same column of a second matrix. So if this is what you're trying to recover, B1 or B2, you have a system of equations to solve where column of a result goes on the right-hand side, column of the original matrix B is your solution. And your coefficient matrix comes from the first matrix in your product, A. Questions on solving those systems? Okay. Now this next problem deals with the transpose and some other terms that I defined earlier. So as is customary, you think of vectors as matrices of one column. So by default, vectors are considered column vectors because it makes things a lot more convenient to deal with them that way. So when you have U and V vectors in Rn and treated as column vectors, so n rows, one column, as I mentioned earlier, U transpose V, that's the inner product, also called the scalar product, and it's also the dot product. So what you do is you to compute U transpose V, you multiply corresponding entries of U and V, and then add up all those products. So it's just a number, because when you're multiplying two matrices, U transpose is 1 by n. V is n by 1. So n's a common dimension in the middle. So the result is going to be 1, because U transpose has one row, by 1, because V has only one column. On the other hand, if you take the outer product, so instead of U transpose V, it's UV transpose, that is a matrix. That's the outer product. So what I'll show you is how do we go about computing. Here we have two different inner products, U transpose V, V transpose U, and then two different outer products, UV transpose and VU transpose. So the first two results will be numbers. The third and fourth results will be matrices. All right. So first for U transpose V. Right. So I'll write out what that is. So here we have U transpose. So U was a column, now it's a row. And then we just have V as is. So this is U transpose, and then this is V. So to carry out the multiplication, you're going to go across this one row, down this one column. And because there's only one of each, you're going to get only one number as the whole result. So I multiply corresponding entries, add them all up. So minus 9a plus 9b minus 6c. So that's the result that you get for this inner product. So now if I go the other way, V transpose U, so I'll write out what that is. All right, so now it's V transpose times U, but then what? We go across this row down this column, we're still multiplying corresponding entries, adding them all up. Well, with multiplication being commutative and all, that's going to give you exactly the same result. So, so U transpose V and V transpose U are the same. But now, what about the opposite type of operation, an outer product? So now I have the first part of a product is a column vector, and then the second part is a row vector. So here I just reverse the order of these things, and it's going to produce a very different result. So what happens here? It turns out to be all possible combinations of products of multiplying an element of this vector with any element of this vector. So notice the first row is the vector ABC all times -9, which is the first element here. Here again, the vector ABC times the second element, 9. Here we have ABC again times the third element, -6. So you can see how the entries of an outer product relate to the entries of what you're taking the outer product of. Similar view of the columns. First column is equal to U times A. Second column is equal to U again times B. Third column is U again times C. So in fact, I can write it that way. Oh. Right. So from the column perspective, all right, so we have is U times A, and then U times B, and then U times C. So it's like you're taking the vector U and tiling it based on the size of the second part of your outer product. I mean, the individual entries of that second part are multiplying what you're tiling. So UV transpose is just U times each of the elements of V transpose stacked next to each other. So in fact, I could write this way. A is V1, B is V2, C is V3. Okay. Now, if you go the other way, VU transpose so just reversing the order. So you're still going to have all possible products, but the result is not going to be the same. So it's not like inner product where it's not commutative. Something is missing here. Oh. Somehow the third row disappeared. Not sure about how that happened. I'll just fill that in real quick. All right. So what we have here is, again, the entire vector U replicated, ABC, 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 multiplied by the corresponding elements of V. So what you can see here is that certain entries, well, actually, very few entries are going to be the same. Like this 1-1 entry is minus 9a in both cases. This like the entries down the diagonal, minus 9a, 9b, minus 6c, those are all the same, but all others are different as a result of multiplying the, taking outer product of these in the opposite order. I wrote it this way so you can more easily see here's where the outer product comes from. So in fact, if I wanted to write down an outer product very quickly, that's what I do. I take first the column vector from the outer product, however many elements I have here, which doesn't have to be 3, it can be any number of elements. I just write out the column vector that many times. Then I go through and multiply the column vector in each case by these elements of the upper vector. So questions about inner and outer products. Okay. Now this next problem, very quick one, deals with one of the properties of a transpose that I mentioned earlier. The transpose of a product is a product of a transposes. So because of that property here, we just apply that to all 3 elements of this expression. So it's just going to be the individual transposes of all of these written in reverse order. So X, then B, then A. There's really nothing more to say about that. Now, this last one, we have a rather unusual matrix that's mostly zeros, but we have these 5s on one of the diagonals. And so it's asking what happens as you compute powers of this matrix. So S squared, cubed, S to the 3rd, to the 4th, 5th, and 6th. Now that sounds like an incredibly tedious process to carry out multiplying 2 5x5 matrices. But if we view matrix S in terms of its columns, then things can be simplified considerably. So take it into account when computing powers of this matrix. What I'm going to do is I'm going to write S in terms of columns of the identity matrix, because E1 is a vector that's all zeros except for the first element, which is a 1, and then we multiply that by 5. So if you ignore this 0 column here, or I mean that's what I have in the first element here. Everything else, it kind of looks like the identity matrix, or most of it anyway. It's just all multiplied by 5. So E1, E2, E3, E4, those are the first 4 columns of identity. So I'm just multiplying them all by 5 and stacking them, stacking a 0 vector to its left. So now that this matrix is described in terms of these columns of identity, that will make it a lot easier to carry out exponentiation. So I'll show you what I mean in computing S squared. So here for S squared, I just write out this S stays the same, and then the other S is written out in terms of these columns, like I have here. Now, using the laws of matrix multiplication, the product would be just multiplying each of these individual columns by S. So I'm just taking this S basically and distributing it through here. Now, SE1, when you multiply a matrix on the right by one of these columns of identity, the product is extracting that column. So SE1 is the first column of S, which is 0. Similarly, SE2, second column of S. So that's 5E1. So I can take SE1, SE2, SE3, SE4. Those are the first 4 columns of S. So I can take these expressions and fill those in here. So once I actually do, actually I'll fill in a intermediate step. Wait, something went wrong there. Okay. All right. So SE1, first column of S, that is 0. Second column of S, 5E1. That's going to give me 5 times 5 or 25 E1. Third column of S is 5E2. Now I'll have 25 E2. Fourth column of S is 5E3. So now I'll have 25 E3. So now I've worked out what all the columns are, and then I can go ahead and take into account what are E1, E2, E3, etc., and actually write out the full matrix. So that's it. That's S squared. So by breaking down by breaking down the product in terms of columns, we could save yourself a lot of work by taking into account what the individual columns are of S. So, any questions about how this result was arrived at? Let's have something in the chat here. Come on. Sorry, it's very slow. Let me check. There wasn't really anything left out. I mean, all the required products were computed. And this one can be cleaned up a little bit, you know, to resemble this, but that's about it. Now we take a look at the original S. Here, where these zeros are, that's the main diagonal. We had nothing there, but then we have these 5s along the first diagonal above it. We squared it. We have 5 squared, which is 25, but not on the first diagonal anymore. It's on the second diagonal above the main one. And you can continue this process to see what S cubed would be. So I can write S squared in the same way. Here we have first column of identity times 25. Second column, third column times 25. And then 2 columns of zeros to the left. So then I can okay. So now if I want to multiply and get S cubed, I need to take this and multiply it by S. So that's what I've done here. I've filled in an S in each of these. But what is this? This right here, SE1, is the first column of S, which is 0. And then here too, we have SE2 is equal to 5E1. So if I continue like I did before in computing S squared, what's going to happen is this. I'm going to get 125s, and now I'm on the 1, 2, third column. So the numbers keep advancing to the right in a diagonal fashion, and I keep multiplying by 5. So you can imagine what's going to happen if I were to continue. That now I can take these numbers, multiply them by 5 again. And now we move to the last diagonal. We have a 625 here on the 1, 2, 3, 4th diagonal above the main one. And really what we're doing is we're chasing all the non-zero entries out of a matrix. So if I then multiply this by S again, what is this? This is 625 times the first column of identity. So I multiply by S. So now you're going to have 625 times the first column of S, which is 0. So once I get to S to the 5th, it's all 0. And if I keep multiplying by S, well, this is already 0. I'm going to get zeros from that point on. So the only non-zero powers of S are S squared, cubed, and 4th. After that, there's no more. So a term to describe this, so if you have a non-zero matrix that becomes 0 after raising it to a certain power, that's called a nilpotent matrix. So S is an example of that. And it's the kind of thing that generally happens when, for example, if I have the main diagonal and everything below it equal to 0, so the only non-zero entries are strictly above it, that would give you generally a nilpotent matrix, whatever entries I had here. Or if I had everything on the main diagonal and above it, all 0, and then I had the only non-zero entries were strictly in this lower triangle, that too would be an example of a nilpotent matrix. So when you have to multiply matrices, it's tempting to just go ahead and use a definition where you have a formula for each entry of a product. And for a case like this, that being incredibly tedious, especially since you can see that most of the entries turn out to be 0 anyway. And it's also somewhat mistake prone. But by treating matrix product this way is like taking the second matrix in your product and breaking it down to its columns, if we're considering one column at a time. In some cases like this one, you can obtain the product more easily. So questions about this last one? All right, so that is the introduction to matrix operations. And then the next section, we're going to learn about the multiplicative inverse of a matrix, and which is very important for solving linear systems, and how to work with that and also compute it. So the homework assignments for sections 2.1 and 2.2 are up already. So be sure to get started studying the 2.1 assignment if you haven't already. So I will stop recording here. So anyone who has questions, I'll stick around. Otherwise, off you go.